Hi, everybody. Welcome back again to another talk at OSA Con. My name is Robert Hodges, and I'll be your host today on our talk, Do We Still Need People to Write Database Systems? This talk is given by Andy Pavlo, whom many of you probably know. He's an associate professor of databasiology at the Computer Science Department at CMU, Carnegie Mellon University. He's also a co-founder of the OtterTune automated database optimization startup. So welcome, Andy. I've attended so many of your talks, gone to visit you. It's so great to have you here. Please take it away, and looking forward to hearing you.
Hey, thanks for inviting me. I really appreciate it. So I'll just say, if you have any questions as we go along, raise your hand or poke in the chat, and feel free to interrupt at any time. Of course, we can take questions at the end. So for today's talk, I'm going to opine about the question of, do we still need humans to write our database systems, or is machine learning so amazing that it's going to solve all the world's problems and we don't need people to build new systems? And so I don't mean that machine learning is going to somehow make a magical database system that can answer any possible question that you may have or not know you have about your data. All that requires an understanding of what's actually inside your database, what your data looks like. I'm really going to discuss whether we need someone to still build the actual internals of a database system, or whether machine learning is advanced enough that it solves all our problems. And so this talk also, because this conference is focused on analytical systems, we're gonna mostly talk about those type of database systems. But I'll talk a little bit about the end of whether the things I've mentioned today are still applicable to operational or transactional database systems. So for the talk today, I'm going to break it up into just 3 parts. First, we'll sort of go and have a quick overview of what the last 20 years look like in analytical databases. Like, what were the major advancements that people had developed to make these systems run better and more efficiently. Then we'll talk about how everyone is obsessed about machine learning now, and I'll highlight some key areas where I think it's interesting. And then I'll finish up talking about where I think analytical database systems are going to go in the next 20 years. Like, what kind of problems do we need to solve to take these systems that people are relying on in their organizations, in their applications, and keep making progress, keep making things better and better. So having specialized database systems is taken for granted now, but there's so many different choices available in the marketplace, and open source and commercial. But it obviously always wasn't this case, right? In the last century, although some specialized analytical database systems existed, like Teradata came out in like 1979. In the 90s, all the commercial vendors had their own flavors of data cubes. But it wasn't really until the last 20 years, in the turn of the century, where people recognized and there was a large enough need for specialized analytical database systems, and that's why the things have flourished so much. And the key reason why all these analytical systems now exist is because there's a larger number of people that need them, and this is primarily caused by the rise of the internet, right? Like, in the old days, there was only a small number of companies or organizations that had what would you call a large data set. In the case of Teradata, they didn't actually install their first 1 terabyte database until like 1992. But again, it was only primarily at the major corporations. But with the internet now, it doesn't take that much work for a small number of people to put a website up or put an application out on a mobile phone and start collecting a lot of data very quickly. And they need to analyze it, and therefore you need you need an analytical system. So this idea of having these sort of separate architectures or separate system designs for operational workloads, for analytical workloads, again, that's not really new. There was a paper from Mike Stonebreaker that came out in 2004, 2005 that talks about how one size doesn't fit all for database architectures, and that you want to build a database system specifically for the class of workload or category workload you expect to execute on it. So in this paper, again, it's a bit old, and he's pushing the stream-based system, but a lot of the same things he talks about are still applicable for analytical systems. All right, so what were the major developments in the last 20 years that separated the analytical systems from operational systems? And so I'll sort of go by by decade, and I want to talk about what I think are the major advancements that came out of these systems, and then we'll see whether machine learning could actually discover these things on its own. So the most obvious thing that came out in the 2000s was the recognition that column-based storage or columnar storage is the proper way or the best way to organize your data for analytical workloads. Right? So say you have a query like this, where you're going to scan the entire table and apply a simple predicate and then compute count aggregation on that. Well, if you store this in the sort of traditional row store way, the challenge is that although you only need 2 columns, A and B, because this data is all stored contiguously, you end up having to read the entire page in with all the columns that you don't actually need, like C and D, right? So you're reading a bunch of data from disk, which is always slow, but you don't actually need it for the queries. And so with the column store, the idea is quite simple. It's that you break up the column or decompose the table into individual columns and store them separately, either in separate files or packed together in contiguous blocks on disk. And so now for this particular query, since I only need columns A and B, the database system only has to read A and B and bring it in. Again, to us at this point, this is 20 years ago. This sort of seems obvious. The first column stores actually go back to the 1970s. There was a Swedish defense system called Cantor that proposed this idea. And the theoretical proposal of the column store approach is from the 1980s. But really, it wasn't until the 2000s where this idea took off. Sybase had an accelerator in the 90s called Sybase IQ that was a column store, but again, it wasn't the standalone database. Where now people are building analytical systems designed entirely around this idea. The other advantage you get from column stores as well is that now, since all the data within a single column are packed together, you can do you can apply compression techniques to reduce the data down further, which is not something you can easily do in a row store. All right, the next other big idea, again, it's not a new idea, but it became more prominent, is the notion of disaggregated storage, or separating the compute portion of the database system from the storage side. And so prior to this, most of the large analytical database systems were using a shared nothing approach, where you had individual nodes that had the CPU, the compute, so the CPU and the memory and the disk. And if you ever had to do a join across different portions of the data, you would have to send messages back and forth through a network. The disaggregated storage in the research literature is called a shared disk approach, is where you separate the compute and the storage. You have individual nodes that will have the CPU and RAM. You do all your query processing. And then there's a shared network connection that has a central location of where to find the data for the database. All right, so the advantage of this is that because now these compute layers don't have the state of the system, because that's down on the disk, you can scale these things up and down very easily without worrying about moving data around. Where in the shared nothing approach, if I have to add a new node or take a node away, then I got to start moving data between them to repartition or rebalance things. And likewise, on the compute layer, I can now scale up the number of disks up and down, even maybe turn the compute layer off and just have store my data in storage without compute nodes and pay less cost. So this idea again existed for a long time. Exadata sort of is this approach from Oracle, but it was really the rise of like the MapReduce programming framework that Google put forth, which was backed by their Google distributed file system that led the site, or that pushed this idea that this is how to store things. And then once the cloud came along, things like S3, this is the performance of this shared disk approach is good enough. It's not like transactional workloads where you need to get things in microseconds. Milliseconds is enough, and S3 is cheap enough where this is a big win for a lot of systems. Of course, the GFS paper from Google, that's from 2003. This is a long time ago. Like I have students that were 1 year old when that paper came out. But again, most of at least in the cloud, most of the analytical database systems are based on the shared disk approach. All right, and the last technique that came out of the 2000s was vectorized execution. And the idea here is that these are instructions that the CPU vendors like Intel added to the CPUs that allow you to process multiple data items with a single instruction. And this is super useful for analytical workloads where you're scanning long strides or long columns of data and applying the same operation or executing the same instructions over and over again. And so instead of having to look at each tuple one by one, you can take a batch of them and then process them all together more quickly to amortize the cost of applying the operation. So this is sort of pseudocode for what a vectorized scan would look like on a table. So now your for loop that's iterating over every single tuple is actually going to iterate over vector tuples. And then you're going to apply the predicate here in our where clause at a vector at a time, and then produce results that you can then store at a vector at a time. right? So just how this is actually implemented is quite simple. So say this is our data set. We have a single column and key and ID. We would feed this key vector into our register or Cindy registers, apply the Cindy comparison in parallel. So it's one instruction to evaluate whether all of the predicates or all of the keys in the vector satisfy our predicate. We store out, we get a mask vector that tells us what keys matched, use an offset array that then do a mapping back to say, here's the offsets of the tuples that match my predicate. Again, instead of looking at every single tuple one by one, we can do this in a small number of instructions and get better performance. So pretty much every database system out there today that is doing analytics is applying some version of this. How aggressive they're doing applying vectorization to their execution engine depends on strictly just engineering. Right? For scans, it's obvious. For other things like hash join probing, aggregations, and things like that, that becomes a bit more tricky. All right, so again, these are the 2000s. This is one of the major things that came out of this. In the 2010s and in the previous decade, I would say that there's sort of two major advancements that came out. The first is just-in-time query compilation. The idea here is that instead of having the database system walk a query plan tree and process each node individually and do lookups to figure out what the data looks like and how to handle it, the idea is instead that you're going to generate a specialized program just for the query that you're executing that is basically hard-coded for exactly the data you're operating on and what the query wants to do. And you run that instead of doing the interpretation, and it's way more efficient. So simple example like this, I have a select query and I have my where clause. I'm doing comparison on a string column and a comparison on an integer column. So the way this where clause will be represented in the query plan is an expression tree like this, where to determine whether an individual tuple satisfies our predicate, I have to walk down the tree, look at the value for the string column compared against the constants, and go down the other side as well. I'm basically interpreting this tree for every single tuple that I want to process in my query. This is horribly inefficient because these are you're thinking like a machine code. You're doing jumps to these different functions, to different locations in the address space of the instructions for this program, and this is like the worst thing to do for a CPU. So instead, what you can do is generate a program that does exactly whatever this where clause wants to do. Like take an individual tuple for a given attribute, compare it against a string, take an integer attribute, compare it against another integer, and then return true if they match. And so what now you can do is you no longer have to traverse that tree. In your for loop, you can either inline this or do a jump to this function and execute it, and that's going to be way more efficient because it's removing all the branching that you would potentially have to do if you're traversing a tree. So in this approach here, I'm showing compilation or code generation for the where clause. That's probably the most common technique that people use. Postgres does this, Impala, ClickHouse, a couple other systems out there do this as well. You can also compile the entire program, the entire query. That's more rare. The only systems that do that are Single Store, formerly MemSQL, and Tableau's Hyper system. There's pros and cons to each of these different approaches. All right, so the other big advancement, I think, from the 2010s for analytical systems is do UDF inlining. So UDFs historically are considered like an anti-pattern for database workloads because it's a function inside your SQL query that's going to execute some kind of procedural code. And from a database systems perspective, from the query optimizer's perspective, that UDF is a black box. You don't actually know what's going on the inside. So therefore, you can't really use that in your cost model estimates about the selectivity of a predicate or so forth. And so it's so bad that there's a bunch of these articles out there that says, UDFs are evil. UDFs are, you never want to use them. UDFs are always going to make your things go, your database queries run slow. But of course, the challenge is that UDFs are really common in enterprise applications. And oftentimes, the only way you can express complex business logic inside of SQL query is through a UDF. So what UDF inlining is, the idea is that we're going to convert a procedural program inside of a UDF written in T-SQL or PL-SQL, and we're going to convert that into a relational algebra representation that we can then inject inside the calling query And then now, since it's just relational algebra, and we already know how to optimize that, because that's what the query optimizer is doing. It takes SQL queries, converts relational algebra, and optimizes it. Then now we can apply all the same optimizations that we normally would for regular queries. We can now do it for our inline UDF. So I'll give it a quick example here. So this is a UDF that takes an integer in and then either spits back the string high value or low value, depending on what the value being passed in is. And here's the calling query like this. So this is just a sort of a tableless query, but imagine the same kind of logic being executed on a per tuple basis if you're scanning a large table. So the paper that describes how to do this inlining came out of Microsoft Research, or called Freud. And again, the idea is that we're converting procedural code like this into relational operators. So the basic idea is that they have transformation rules that can convert this function into the corresponding SQL query. In this case here, they're using lateral joins to actually represent the different blocks inside of the code. But then now, since this is just a SQL query, we run it through our query optimizer as we would with any other query. And so now we get all the advantages that the data system has to reduce the complexity of UDFs for free. We don't have to write special code that optimizes this. If we can get it to a SQL form, we can just run our regular optimizer rules. So we can do dynamic slicing. In this case here, we know we're executing it with 5,000, so we can remove the parts that we're never going to touch. Then we can do constant propagation and folding to get it down into a nested query instead of a lateral join. And then we end up with, after doing dead code elimination, we can remove the adder select statement and get it down to be exactly whatever the output should be. So this is a trivial example, but hopefully you can imagine, like, for more complex UDFs in very expensive operations going on a large table, this kind of optimization is a big deal. And so Microsoft actually ships this now in SQL Server 2019. I think they announced this year it's also available in the Azure, the cloud version of this. And in their analysis, they've looked at basically every single UDF that anyone's ever executed on Azure, and they think this inlining approach can support 80% of them, right? For some UDFs that have like update statements or insert statements or dynamic SQL where you concatenate a bunch of strings then invoke the query, you can't do this, but there's still enough UDFs out there that do fit the within the match the patterns that this thing is allowed to optimize. So I think this is amazing. I think this is a game changer, because the performance benefits are quite significant. Of course, the problem is that this method is sitting in a patent minefield owned by Microsoft. So at this point, only SQL Server is going to have it. There is some research techniques where you can convert UDFs into a bunch of CTE queries, common table expressions, that get you some of the way there. But I think the Freud approach is the best thing out there now. Okay, so let's talk about the way the world is now. So, I talked about a bunch of techniques that people have developed, and they were all developed by hand, meaning really smart people looked at the hardware, looked at the workloads that people were trying to execute on these databases, and made decisions about how to design these systems. And so where we're at now in the 2020s is everyone's focused on this idea of a learned component. And a learned component is where you're going to implement some portion of the database system internals or some aspect of the database system's behavior using a piece of software that's been developed through machine learning, where you observe previous execution traces or behaviors of the database system, and then you train a model that can then generate or devise what is the correct strategy to use for future invocations of that component, right? As opposed to having a human sit down and say, okay, if the data looks like this, do that. If the data looks like this other way, do this other thing, right? Instead of doing that, you can build models that can learn automatically what the right thing and the best approach is to perform some operation. So the most famous of these learned components is the learned index. So a traditional index, like a B+ tree, you're given a key and it gives you a location into some array. The array doesn't have to be sorted, but for simplicity, assume it is. So what a learned index is that you're replacing the physical data structure of the B+ tree with a model you've trained by observing the positions of keys in the sorted data array, and for a given key, where does it exist? And you can train a model on that regression, and basically now predict if for a given key, where is it likely to appear in my sorted data array? And so, my picture here does not really maybe indicating what the difference is, but in the B+ tree, you have to make copies of the keys on these upper nodes. But in the model, you don't have to have all that redundant information. Each index itself could be more compact because you're not storing these keys. It's just weights inside the neural network or whatever model you're using. And it may not be an exact match, but that's okay for some workloads where you just need to be in the right location. And it's better than having to scan everything. So, as I said, learned indexes are probably the most, at least from a research perspective, it's the most active area. Partly because you can build a learned index and do a bunch of experiments without having to integrate in Postgres or SQLite or whatever database you want. You can just run in your own little environment and see how much it helps. A bunch of the other things that people are applying learned components to require surgery in a database system to see whether it's actually beneficial or not, and therefore those areas are a little less less explored. So besides the learned indexes, people have been using this for sorting algorithms, hashing algorithms, scheduling. There's a lot of work done on query planning, because that's traditionally the hardest problem in database systems. A lot of work done on cost models and cardinality estimations. And then there's work done on sort of the configuration and management of the database system itself, either through knobs, the physical design, like picking what indexes to build and so forth. So there's a lot of work to be done in this area. And I don't have time to go through all of it. I just want to highlight two of them that I think that are the most promising. And that's for cost model for query planning and then knob tuning, which is what OtterTune is based on. All right, so the idea of a learned cost model in your database system is that we want to either replace or supplement the existing cost model that the data system is using in its query optimizer with one that can learn from prior queries being executed. Meaning, like, the cost model says X, we run it, and then we see the cost is really Y. Then we want to have a feedback mechanism to say, hey, you got that prediction wrong. Here's what it really should be, so that when future queries come along, you can make better choices. So let's say I have a simple join query like this. So the traditional optimizer is going to generate a bunch of different alternative query plans that it could use to execute that query, say by replacing what join algorithm to use. Do I want a hash join, nested loop join, or assert merge join? And so again, a traditional optimizer would then evaluate these different plans and predict which one it thinks will have the lowest execution cost, and picks the one that obviously things will run the fastest. And so we're still going to do the same thing here in a learned cost model, but now we're going to have our separate cost model that we're using to predict what the cost is. So we're sort of replacing that one piece of the system of the query optimizer, but we're still letting it do whatever the search algorithm wants to do to figure out what the different possible query plans it could choose. Then we go ahead and execute this. We'll produce a result that we send back to the client, but then we're also going to observe what was the actual runtime behavior of the query plan that we chose. And then we'll feed that observation data into our model trainer that can then propagate the update to the model we're using to predict our cost. And that way, when future queries come, again, we've seen prior executions of something similar, and we can make a better prediction which one is actually the best. So obviously, the hard part is the feature engineering, meaning like how to identify what information about the query plan, about the environment, about the distribution of the data that we want to incorporate in our model, so that when we see future queries that maybe not look exactly the same, where our distribution has changed, we insert a bunch of data or delete a bunch of data, but as the ground is sort of changing underneath us, we don't have to start over from scratch, and we can still reuse some of the data we've collected, or the observation data we collected from previous queries, and make better decisions on future queries. So there's a paper in Sigma this year that actually won Best Paper Award on a system or a framework called BAO that discusses how to incorporate a sort of a learned cost model like this in a real data system like Postgres and so forth. But this is obviously not the first time this idea existed. As far as I can tell, when the first ideas or the first papers in this space that actually try to learn from query execution to make better cost model decisions, what came out of IBM for DB2 on a project called Leo. Now, the early version of Leo was a bit more simplistic. It wasn't using machine learning. It was just, would run the query and try to update the cost, the query optimizer's built-in statistics and histograms that it's maintaining to compute costs. Whereas the BAO approach is actually trying to train machine learning models. But the basic idea is the same. So I was saying, I'm the most bullish on this kind of stuff, using machine learning for query optimizers, just because it's such a hard problem, and it's something that a small amount of benefit can make a big difference. So I foresee, at least in the commercial systems and open source systems, techniques like this, getting adopted more quickly than others. All right, so the other area that I think is interesting, again, I'm biased because this is my own work, is on automatic knob configuration tuning. So a knob is a runtime parameter that the database system exposes to you to allow you to change its behavior, like buffer pool sizes, caching policies, log file sizes. Every database system has these different knobs. They exist because as the person that was writing the data system had to make a decision about how much memory to use for a hash table or something like that. Rather than putting #define in the source code and assuming that it's good enough for everyone, they're instead going to kick it off as a configuration knob and assume that somebody else more knowledgeable about how the application wants to use the database is going to come along and be able to set it correctly. Of course, that never happens, and people often run with the default. So the way this works is that you have some kind of agent that connects to the database, retrieves the current configuration and runtime metrics of the system. So pages read, pages written, locks held. These are the internal performance counters that every database system maintains. The system is going to then store that in its internal repository and then train statistical models that'll predict how the database system's performance will change as you start tweaking and making changes to those configuration knobs. And so this model basically looks like this, where you feed in the knobs, the metrics, and maybe some additional information about what kind of hardware the system is running on. And then it spits out what he thinks the expected performance will be for the, for this setting. And then you run gradient descent on this, and then produce a new settings or new values for configuration knobs that you then send back to the agent, who then installs it, flushes the changes, and repeat the process. So you can just do this over and over again. At some point, the model will converge when it thinks it has the best configuration for the given database right now. So again, as Robert said in the beginning, this is something that I've been working on at the university for 6 or 7 years. And then in the last year, we spun this off as a new startup called OtterTune. And what is maybe sort of the most happy about this, the startup experience, is that the findings that we saw in the lab are actually, the techniques we developed in the lab still work in the real world and real applications where we have a less controlled environment. So this is just some numbers we have from running some workloads on TPC or Postgres and MySQL on RDS. And you can see that, comparing what the OtterTune configuration is against the default configuration that Amazon gives you in RDS, in Postgres, we're doing almost 3x better, and MySQL, we're doing 4x better. Right. So again, this is all just done through machine learning. It doesn't require any changes to the application. It doesn't require us to actually look at any sensitive data. We can just do all this through our metrics. Okay, so what are some of the challenges that we're going to face in the next upcoming decade about getting these learned components actually implemented and used in practice? Well, the first thing I would say is what we're missing is fail-safe mechanisms, meaning we don't have a way right now in these components to, first of all, recognize when maybe the models go bad or when it's making bad choices, and then have something potentially to fall back to until human could come and make corrective actions. Right? It doesn't help me that I have this great machine learning algorithm that can use, or machine learning model that makes great decisions 99% of the time about the best way to execute my query. But then the 1% time it gets things wrong, can get things horribly wrong. And if that's the case, no one's gonna trust it. And so I think what needs to happen is there needs to be some way to identify in these systems automatically that things are not going the way they should be going, and then have something to fall back to. And it could be these traditional heuristic-based methods that exist in systems today. So basically, I'm going to say is even if you have a learned cost model, you don't want to rip out the old one. You want to keep them running side by side. In the case of the BAO approach, they do have that. The next is the ability to explain to humans why the machine learning models are making a certain way. I think this is more important in the beginning because humans obviously are not going to trust machine learning based approaches right away. And so they want a way to, to understand why is it making certain choices and potentially, prove them one by one to make sure that, it doesn't go off the rails. So having the ability to provide a human readable explanation about why certain choices are made is really important. And this is a hard problem. This is not just for databases. This is a sort of unsolved problem in machine learning in general. The next one is more of a philosophical question that we've been thinking about, but I don't have an answer. And that is, how do we incorporate feedback or input from a human that may potentially negate or override choices that the machine learning algorithms make? And I say it's a philosophical question because at the end of the day, a human is, humans are the one that sort of cares about the software running. And a human is actually paying for the hardware and paying for the software itself. So who actually makes the final choice? Like if a human comes along and says, hey, I really want to build this index on this table, but the machine learning algorithm says, hey, that's actually a bad idea. You don't want to do that. Who should win that fight? And I think the middle ground solution is that you do whatever the human wants you to do, but then you watch what they ask you to do. And if it turns out that it was the wrong thing to do, then you come back with an explanation of why you reversed it. But again, if they're the one with the credit card, they might not like that. And the last one, again, is an important problem for all aspects of machine learning, and that's being the transferability of the things you learn from one scenario, one environment, and applying it to new scenarios. It doesn't help me that like if Amazon's releasing a new instance size on RDS every single year, or they're putting out new Graviton trips, or they're putting out new hardware. If I have to relearn everything from scratch every single time there's new hardware, then it's going to be really expensive. So being able to apply knowledge from one area to new areas is super important. So the high-level question, again, that this talk was all about is, do I think machine learning is going to replace the need for humans to build new database systems? And of course, I'm super biased because my research areas in database systems, building them, I teach how to build database systems. And so if this was true, I'd potentially be out of a job, but I still think the answer is no. And again, looking back at all the things we talked about in the last 20 years, there really isn't anything that a machine learning algorithm could potentially uncover on its own. It was it was this solid engineering research work being done to make these things happen. But now with these learned components, since that is machine learning based, do I think if we just replace all the things that are written by humans, assuming that they work really well with machine learning based ones, are we done? Is that it? Or what else could we do? And so with this, I want to sort of think about two challenges that I think we're going to have to solve in the next 20 years to achieve the holy grail of a fully autonomous database system, and then go beyond what we can even do today. So the first challenge is how to remove humans entirely from any decision-making processes for certain tasks that do not require a human to make a value judgment about some external cost. And so what I mean by a human value judgment on external cost is if there's something outside the purview or the understanding of the database system that could have a detrimental effect or costs, have a cost, and it's not something the database system can easily know about, then the decision about whether to apply a certain action that could incur that cost has to be done by a human. So for example, if I have my company and I'm running my website on a database, and the machine learning algorithms figure out, hey, if you turn off fsync for disk writes or transaction commits, you're going to run a lot faster. But of course, that means if there's now a crash, you might lose the last 100 milliseconds of data. That's an external cost that the data system can't know about because it doesn't know whether your company is going to go under because you lost the last 100 milliseconds. So it's those kind of things where we still need humans, but everything else should be done, I think, can be completely automated. But the challenge we face right now is that everything for the most part, that I talked about are all reactive approaches, meaning they've looked at things in the past and they sort of design the system and they make optimizations based on those prior observations. And they can't look forward and say, well, what should be doing in preparation of what I think is going to come in the future? And that's what humans are doing today. You're doing capacity planning. You're doing preparation for Black Swan events like Cyber Monday or Singles Day in China, right? Humans know that those things are coming up, knows that they have certain patterns in their workload, and they prepare accordingly. And that's not something the current methods can do now. So the way to get there is actually through what we're calling a self-driving database system, and is actually heavily influenced with how self-driving cars work. So a self-driving car is sort of comprised at a high level of 3 parts. The first is you have a perception model that can perceive what are the other cars that are around it as it goes down the road. And then the next is an action model action models that then can predict how the different parts of the system behave as you make changes to them. If I turn the steering wheel this way, what happens to the car? If I hit the brake, what happens to that car? And I can use that to figure out what are the different choices I can make and how that will affect my position and my trajectory on the road. And then there's a planning approach where, given the models and given the action models and given the forecasts or their perception models, I know I can predict where other objects on the road will be in the future. And if I have my end goal of moving the car to this position in the next lane, I can then predict what are the different actions I should take to get there. So again, this is the high level how self-driving cars work. It's obviously much more complicated than this, but we can be motivated or inspired by this to do the same kind of things for databases, because it's at a high level, it's essentially the same thing, right? Instead of looking down the road of other cars or other objects, we care about the SQL queries that are showing up. And now we can build forecasting models that know what kind of queries and at what cadence and what frequency are going to show up in the future, and we can use that to predict what we're going to have to prepare for later down the line. For the action models to understand how the data system is going to behave as I make changes or as I execute queries, you can decompose its internal mechanism of internal components into separate models that you can then train that will predict how much hardware resources they're going to consume when they do certain things. If I execute a query that's going to read 1,000 tuples or 1 billion tuples, how much RAM am I going to need? How much CPU am I going to need? And they can use all this information to do action planning to say, here's all the different actions I could apply, build an index, drop an index, tune a knob, increase or decrease my provision IOPS on Amazon. And I have my end goal of what I want to achieve. Like, I need to make sure the system doesn't run out of memory, that I'm running with the lowest cost, or the best latency. And then I can choose a bunch of different actions that'll get me there, choose the best one, and then apply to the database, repeat the process over and over again. So again, this is sort of the high level path that we're going forward in the research back at Carnegie Mellon on building what we're calling a self-driving database system that sort of incorporates these key components. And I think this is what you need to have a truly proactive system that doesn't require humans to do planning ahead of time. You can do everything through this. The last challenge I think that's going to be super interesting to solve is, can we start to uncover different techniques or system designs that are not known to humans today, or not something humans can think about, but we can find these things automatically. So you see this approach used in other areas of science. There's actually an article from a few days ago from Scientific American where sort of scientists in biology and chemistry and other areas are using machine learning to uncover different patterns of the data or things that they should experiment on that would not easily perceive themselves. Like, they feed a bunch of radiology information into it and identifies, here's some interesting characteristics to explain why people have a certain disease versus people know that they don't have the disease. So I think we want to apply the same techniques to database systems and try to be able to find things that are counterintuitive for us as humans that know the internals, but that may end up being the right way to execute a query or store data a certain way. And it's sort of similar to the optimizations that I talked about at the beginning, where a lot of them were converting traditional implementation methods to what was easy for humans to reason about and implement from an engineering perspective into what was the best way to represent the data or execute queries for the hardware. Like, the vectorization stuff is sort of not how most people write databases when they first start, but to convert the engine into a vectorized format is actually the best thing for a superscalar CPU, and therefore that's the way you should actually implement things. So I think these are the kind of things we want to uncover in the future going forward. But of course, to do this, you need your database system to have the proper APIs exposed to the outside world that allow you to observe the right information you need about its behavior, as well as to make changes to it or instrument the internals so that you can make tweaks and do it sort of brute force search to find the different combinations of things. All right, so lastly, as I said in the beginning, I want to talk about what are the things that, how does this apply for everything we talked about is for analytical systems, how does it apply for transactional systems? And what I'll say is that a lot of the same learned components are still useful for transactional systems, but I think there's going to be less of an upside or less benefit than you get for an analytical system. And this is because oftentimes what's the limiting factor in the performance of a transactional system is sort of the fundamental property of physics, or the material world, like the speed of light. Like if I have run a transaction in two different data centers, I can't magically make network packets go faster than the speed of light. So I'm always going to be bottlenecked on those things. So I think going forward, though, like to get even better benefit is going to require us to be able to reason about higher level information about how the application wants to use the database and execute queries that are not readily available for us now. So what I mean by that is if you can know how the application uses the result of a query, then that could potentially inform you how you actually want to execute it. So an obvious example would be you see a bunch of ORMs where they generate SQL queries that have select stars in it. But if you can actually understand what the application was actually doing with that data, you would see it maybe it's only using half the column. So you don't need to ship all the the entire tuple over. You do a projection. It's only send a portion of it. So for analytical databases, I think this is less of an issue. I think there's more stuff to be done in making the systems go faster just by looking inside it itself. Whereas the transactional stuff, I think you have to look outside, which is a hard problem. All right, so to finish up, I think that where we're at today is that the machine learning methods are making better database systems. But at the end of the day, you still need someone to implement those components to incorporate these machine learning methods. You still need something to write the for loop that then can call whatever machine learning thing you want to call on data as you run it. And as I said at the end, I think there's a bunch of unsolved problems about how we can use machine learning to find different techniques or do certain things that humans are not readily, easily able to do today. Okay, so with that, I'm happy to answer any questions. Thank you.
Thank you so much, Andy. Excuse me, this is Robert back again. Wonderful talk. There was a question from Mayo, which I think you kind of touched on toward the end, and it is turning the question slightly, do we still need people to design and administer databases? So are there optimizations that go beyond the database itself that you can foresee?
So the question is, do we still need a DBA? So I would say yes. There are certain optimizations that we don't want machine learning algorithms to do on its own. And again, this gets back to this external cost. Again, turning off fsync is an obvious thing. You can do it, but it may not be the right thing for your company or for your product. For database sort of high level design, I mean, currently there is not good existing methods, the automated methods to handle this, because again, I think it requires the ability to infer deeper meaning of how the application is going to use the database. Furthermore, if there's something that's going to happen in the future that some kind of automated method can't possibly know about, like, oh, I need to have these two tables split. I can't denormalize them because I know that a month from now we're going to add this new feature that needs it. That's really hard to do. So I don't think DBAs go away. It's where machine learning is going to help is the sort of the grunt work tasks like knob tuning and so forth that we can take off their hands so they can pursue more fulfilling things.
Great. I had another question which came up when you were talking about the automated car examples. One of the problems that driving is so difficult is it's such an unconstrained problem. So for designers, do you have any tips for how people should practically design databases to make them more amenable to machine learning optimization?
Yeah, so there's so actually this is, go back. This is the paper that I was highlighting that we wrote in this year. So this is on our website. So this is a bunch of rules or design philosophies that we developed in trying to build our own self-driving database system that we found that the existing systems were deficient in. I'm trying to think of a good example of this. So one is like for certain knobs, sometimes you apply them and you don't have to restart the database system to be applied, but they don't take effect immediately. Like, so MySQL, I think if you change the bucket pool size or something, it'll size it incrementally. So it doesn't happen immediately, but it'll just do this gradually over time. The challenge with that one is if now you see a degradation in performance while it's doing that change, you don't know whether it's because of something you did or it's because the workload has changed. So some of those aspects make things more challenging. So just having an API that exposes, hey, I'm doing this and then I'm done, like, so you know what the boundaries are of certain changes if they don't happen immediately is super helpful. And of course, the most obvious thing about all of this is if you don't require restarts, that makes everything a lot easier.
Yeah, in other words, just make things, no restarts, and then of course, make things more deterministic so that you can reason about them a little bit better.
Yes.
Great. We're actually over time. Oh, here's a, not really a question, but rather a note. Natural language models such as OpenAI Codex already can translate natural language into SQL, potentially can simplify the job of DBAs. I mean, goes beyond what you've said, but it does sound like there's maybe other ways to think about this problem. Is that?
So I mean, the holy grail, what you really want your data system to do, like there's two problems. There's the administration and the system design. That's what this talk was about. There's a whole other problem of how to automatically decipher or find interesting patterns in your data that you may not know about. Like the idea is, can you get your data system to tell you things that you don't know but you should know? The text to SQL query, that's sort of like, can I answer a natural language question and convert it to a SQL query? That's still, you have to know what question to ask. We're not at the point yet where we can do sort of alerts and automatic extrapolation of new knowledge from data without you having to put do any feature engineering. Great.
We're over time. So Andy, thank you so much for a wonderful talk. This survey was great, and the ML work that you're doing at OtterTune sounds really exciting. And believe me, you're right. I mean, the performance gains by changing little things can be just huge. So I think your point about that the cost benefit here looks potentially really great is something we'll try and push into some of these open source databases we're working on.
Absolutely, yes.
Thanks, Andy.